today we are very happy to have an external speaker, Professor Siegmund of Uni Passau, come and visit us, and she will talk about controlled experiments, as you can see. She has, interestingly enough, a diploma in both psychology and computer science, which of course makes her the perfect computer science researcher, certainly when it comes to empirical methods, or as we call it, confirmatory research. And so she's right now in Passau, as well as a professor in software engineering, computer science, and she will talk about controlled experiments. I think I will simply hand over to her. So thank you very much for being here, and we're looking forward to your talk.
Oh, thank you. So also it's not as much as I am talking, but like we are talking, so I don't like to talk too much. That's why I have many questions for you, and also when you have questions anytime, just raise your hand. So it's designed to be more like a discussion. Okay, so controlled experiments. I have some examples of what can be controlled experiments. So like when you're watching stars in the sky and you wanted to detect planets, this is also kind of an experiment because you are observing something and you want to observe the outcome of something. Or when you have a new warp drive in your spaceship, you want to evaluate that. It's also kind of an experiment. Or when you have two teaching methods you want to compare, you can also form two groups, and then you also have a controlled experiment. Okay, so what are experiments in general? They're defined as a systematic research study, so you do some research and you are systematic about that. You have factors in that study, you intentionally vary those factors, and you try to hold everything else constant during that time. And then you observe the result of the systematic variation. So when you compare two teaching methods, you observe the result of the teaching method, so how students learn based on this new teaching method. And what I want to do here is focus on human participants, so always when you have humans in your experiment, but all that stuff we are talking about here also applies for non-human studies. So like when you want to evaluate the performance of computer system or your new warp drive, and also all the methods here apply there as well. So if you're interested in that stuff, a bit more about the historical stuff, you can read something about that. It's only available in German. I guess there are translations, but I'm not sure about that. Okay, so when you design an experiment, you have these stages you go through. So first you define what you want to measure, what you want to observe. You define your hypothesis that you want to evaluate. You define the variables that you measure and the variables that you observe. And based on the objective definition, you can then select an experimental design. So how you arrange the participants into groups, what exactly you are measuring and observing. And then when you have planned your design, you can execute the study. Hopefully nothing goes wrong, but there will always be something wrong. Then you get the data. You have to analyze the data, and then also very importantly, you have to interpret the data. So what do the results mean for the hypothesis that you defined? And through this talk, we will go through all the stages, depending on the time we have, depending on the discussion that will emerge, and then we talk about each stage in detail. Okay, so we have a running example for each stage. We will discuss the problems and solutions that occur in each stage, and there will always be problems. And what I want you to learn here is that you get a feeling for how to design experiments. So when you have your research question, that you know what to do, how to arrange your participants, that you can really answer your research question. And also, very importantly, that you know what to do with the data. So you will get a lot of data, and then you have to know how you can handle the data, how you can analyze the data, and what the conclusions there are that you can draw from the data. Okay, so I will have a running example here. And typically we have comments in source code. You are computer science, you know source code, right? Okay, good. So you know you have comments in source code, or you don't have comments in source code, and you have a feeling that they help or that they don't help. And so these are typical questions that you can ask when you have comments in source code. And what I want to focus here is on the first one. So do comments make source code more comprehensible? And that's the example that we use through the talk. Okay, now I'm at the first stage, the objective definition. The first thing that I need to do there is decide about the variables. First thing, the independent variable, also called the factor or the predictor variable. And this is the one that you intentionally vary. And this is also the one that influences the dependent variable, so the thing that you are observing. So in the running example with the comments, what is the independent variable here? Exactly, the comments. And specifically, okay, so when you have the independent variable, you have to find somehow a method or operation with how to measure it. So for the independent variable, it means there are different different levels. So one example would be that I have the presence or absence of comments. So in one version there are comments, and the other version, so the other level is there are no comments. Do you have examples for other versions of levels for comments?
Short or long comments?
Short or long comments?
In the order where I inserted, if they are at the beginning of a piece of code or embedded into it.
Exactly, the position of the comments, also the quality of the comments, good comments, bad comments, useless comments. Okay, now for the dependent variable, also called the response variable or the outcome of the experiment. So in the example with the comments, what would be the dependent variable? Okay, comprehensibility of the code.
Problems with using the code right.
Problems with using the code, okay. Also the maintainability, if I want to observe that, or the development time. These are all examples for dependent variables. Okay, also for the dependent variable, I have to operationalize it, so I have to find a measure, how to measure the dependent variable. How would you measure program comprehension or the comprehensibility of source code? Yes. Development time. So you would give participants a task and then measure how long they need. Okay.
Yeah, we'll have a large amount of participants picking the code and having a survey where they have to answer questions of the code. Then have to, some of the participants have the code with comments and some without.
Mm-hmm.
The number of participants is large enough, maybe we can reload the session.
Okay, so what kind of questions would you ask them?
Well, they would be code-specific questions like, how does this work? What does this variable mean in this context? Or what does this variable do?
Okay, so comprehensibility questions. Okay, that's another option. Any other ideas? Yes.
Make it multiple choice and offer 5 to 6 alternative explanations.
Okay. Can also do that. But of course, then you have to really be careful how to design the questions and the answer. Again, the open questions, they're really good for measuring. But then again, analyzing the open answers is, of course, a very tedious job. Okay, you always have to weigh in the advantages and disadvantages. Okay, I can also give a subjective rating. So I just ask participants afterwards how much they understood of the code. Then I can have a scale like a bit, nothing, or everything, which of course is easily biased. I can give them any kinds of task. I can ask them, okay, comprehend this piece of source code. Or if I would execute this piece of source code, what would be the result? Then I can analyze the results of these tasks and can also assess the time they need to answer these tasks. And I can also use the think aloud protocol. Anyone an idea what that is? It's It's really a speaking name. Yes.
Well, I'm just guessing you would, like a code explanation, they would go through the code and explain it while you're sitting there, and then you would understand it?
Kind of, yes. But think aloud is not specific for the source code, but in essence, participants just speak out their thoughts. And you can do this for all kinds of experiments that you want to do. And the advantage is that you can really, you can observe the thought process of the participants. But of course, again, you have a lot of data to analyze. Okay, then when I'm sure about the variables, I need to define hypothesis about the experiment. So I have some kind of expectations about an outcome. Maybe I have a theory on that really comments help the comprehensibility of source code because maybe they just add another level of explanation to the source code, and then they should help participants to understand the piece of source code. And based on the theory, I can derive hypotheses. Maybe also you have had experience during your time, during your studies, when you implemented something, you know, okay, comments always help me to understand the source code, and then you also have kind of an expectation about the outcome. Important thing is that the expectations that you have, they must have some kind of reason. You cannot just say, well, I think it's that one. You always have to think about why. And then there are also cases when you have no idea what the outcome would be, so maybe comments help, maybe comments don't help. Then in this case, it's okay to just define a research question. So do comments help to understand source code? But in any case, you have to give this some thought in the beginning, how the variables interact with each other, how they influence each other. It's very important. Okay, so I have some examples for hypotheses. What do you think of these? Are they good hypotheses? Yes.
No, they're too unspecific. I think there should be a bit more reasoning behind them.
Okay, too unspecific, and you say there's no reason behind them.
Yeah, somehow it could be better explained why are they bad and.
Okay, so let's assume I explained them like bad comments. They confuse developers, so they are bad for comprehension. Would these be better hypotheses? It's the first part that you mentioned that they are not specific enough. That's more important here. So what? Yes.
I think it's also a point about what is a bad comment or how do you define a bad comment overall, because is a bad comment a comment which has bad grammar, or is a comment bad comment a comment which has no meaning, or what is a bad comment first of all?
Exactly.
So nobody knows what a bad comment is.
Exactly. Also the same counts for good comments. What are good comments? Okay, now what does bad for program comprehension mean? Yes.
Yeah, that would have to be specified too. So is it a bad readability, or in which ways is it bad? Does it increase development time? Does it lead to more questions, or having to ask the programmer of the code?
Exactly. So it's also not specific enough. So I have no idea what are good or what are bad comments with these hypotheses. I don't know what bad for common comprehension means. Are they slower? Do they make more errors? Do they answer all the questions wrong? I have no idea with these hypotheses. So one important thing about hypotheses is that they must be falsifiable. That means if they are wrong, I must be able to design an experiment to show that hypotheses are wrong. When I have unspecific hypotheses and I have data based on the experiment, I still cannot answer the hypothesis because it's not clear what good or what bad means. So I always have to be as specific as possible to have falsifiable hypotheses. So if you're interested in that, there's a nice, I think it's from a book, The Logic of Scientific Discovery from Karl Popper. It's a bit philosophic, so lots of talking, long sentences, but it's really interesting, really an interesting read. Okay, so how can I make better hypotheses?
Can you repeat the question?
Okay, how can you make better hypotheses? What would be examples for better hypotheses based on the comments and the program comprehension?
according to the hypothesis.
Okay. You want to give it a try with the definition? Yes.
I think if you include the definition of what is good and bad, then the hypothesis becomes a three-line sentence or hypothesis.
That's true. Okay. Exactly, you're right. 3-line sentence. Okay, I'll just give it a try. So, comments describing each statement of source code have no effect on the response time of understanding source code. So I've specified the comments. Comments just describe each statement. So if I have a statement like for a for loop, the head of the for loop, and the comment just describes, okay, this is the head of the for loop, I initialize the variable, blah, 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 okay, has no effect on program comprehension. And also that, I have specified that, so the response time of comprehending the source code. And then I can have bad comments, an example for bad comments like comments containing wrong information, which actually often happens when a source code evolves, the comments often do not evolve. And then you have incorrect comments about the source code. And an example for good comments could be that comments that describe the purpose of the statement, so why a statement is there, they speed up the comprehension process. And these are examples of, I don't know, good, but definitely bad hypotheses, because they are falsifiable. Okay, now you can ask yourself, why do I need hypothesis? Why don't I just measure and see what the result is? And actually, when I tried to publish an experiment in the beginning, I really had these comments as review comments. Really, reviewer asked, why don't you just measure and see what the result is? This is really, interesting about the competence of the reviewer on empirical studies, because the hypothesis, they drive everything else, the experimental design. They drive how you arrange the participants, what you measure, what tasks you have. They determine everything. And also, if you don't have a hypothesis, there's the danger of fishing for results. An idea what that means? Yes?
Yeah, if you just measure anything and you just got a bunch of numbers and don't know what these numbers actually mean, and you just pick random numbers which you think can measure something.
Exactly. Also, you can look in these numbers until you find something interesting. So I just analyze and do all tests that I can think of on the same data, and then suddenly I find something interesting, and then, yay, I have a result, but I'm really fishing for results. And this is not a good thing, because often you cannot replicate these results. They only hold for your specific data set. Yes?
I have a practical, more or less practical question.
Yes.
Because sometimes, or maybe more often, you have a data set given, which is given by constraints you cannot change. Yeah, for example, the amount of data you can write on the hard disk, and you cannot buy more hard disks,
Yes.
even if you want to. So, of course, it's fishing for results, because it has a large effect on your experiment.
Yeah, but it depends on what you want to do with the data. What do you want to do with all the data? You want to answer a hypothesis, evaluate something?
Okay.
So, I mean, even when you have a data set, you can still, before you do anything on the analysis, you can still think about what do I want to do with the data set? What are the statements I want to make? What are the conclusions I want to draw? And then only look at the data and decide on the measurements. Yes?
So let's say I do some research with the hypothesis, like normal, but at the end of the research I find something additional that isn't really covered by the hypothesis that I maybe encountered on a random node. What would be the right procedure then? Would I still include it into the paper or make a new one?
Okay, interesting question. I think it's definitely okay to just mention these results, but definitely explicitly describe that it happened, a result by chance, and then describe it in this sense. Always have in your mind, okay, just coincidence, this results, I need more studies to definitely check the results again. But it's definitely okay to report the results. And yes.
So by fishing for results, do you mean more pie hacking, finding correlation between things that may not actually be there,
Yes.
or actually looking for something that answers your specific question that you had beforehand?
Both, actually. So p-hacking, I guess we will talk about that a bit later, what that means. But also looking into data until you find something to confirm your hypothesis, also fishing for results. So every time you look in the data and apply more tests than you have planned beforehand, this is fishing for results. Okay. Any more questions on the objective definition? Yes?
Sure, fishing for results to answer your question, that is a bad practice?
Yes, kind of. If you fish, if you do several tests, I mean when you do significance tests, for example, to observe whether there's a difference and to determine whether it's really significant, and you do first this test and then it's negative, then you do another test, it's negative, and you do yet another test, also negative, or maybe a fourth test, and then you find, okay, it's positive, that's fishing for result. I mean, you cannot always specify the test that you want to do because it also depends on the data. But then you can also define beforehand, okay, if the data have this distribution, I use this test. If they have this distribution, I use this test, and so on. So you need to define beforehand as much as you can, as specific as you can, the analysis procedure beforehand. Okay, yes?
There's a question online.
Yes.
Min Fung is asking, where is the line between confirming the hypothesis or fishing? Is there
It's difficult to say. It also depends on the data that you have, how large the data you have. And sometimes there might be cases when you really have a huge data set and you do not know beforehand what kind of procedures you want to do on that. So it's a fine line. You can do kind of tests, and you can also do more tests than you planned, but then you have to specify that. And you can also do kind of an exploratory approach, so explore the data, what is there. But then again, you have to be careful not to drift into fishing for results until you find something interesting. And especially when you're exploring, you need to do further studies to confirm the effects that you found. So it's not a straight cut, but there's a continuum definitely. Yes?
So I think the easiest case for fishing for results happens if you actually have a sequence of experiments, and from one to the next you start varying parameters because you think or you hope you will find something in a particular corner of the experiment.
Yeah, but if you have really assumptions or expectations about that this one factor has an effect, then again it's okay. Then you do a family of studies, so like kind of like replication studies, which are really done in medicine when you have a new drugs. You do exactly these kind of studies. You vary just a specific factor.
If the systematic variation is planned before you start the experiments, if you adjust based on the results, wouldn't that be fishing for experiments?
It depends. If the data really suggests that, without really fishing till you find something, it's really a fine line, and you really need a lot of experience with all the data. Another online question?
No, not online.
Okay.
So let's say I'm doing exploratory research, so I don't have like a very specific thing I want to find, but I just want to understand the domain or the question. Or if I just want to understand the concept or the domain better. In this case, how can I set the condition when I should end my research? So it doesn't become fishing, so I go until I find something interesting, but rather there's some type of finishing condition when I decide to finish.
That's a tough question. So again, you need to define beforehand how much you want to go with the data, how many information you want to extract, for example. You need to define as much as you can beforehand what you want to do, and then you stop. And after exploratory research, it's really important to do confirmatory research, so to try to design an experiment to the results you found. Again, there's no straight cut. You just have to, based on your experience, the knowledge that you have about the domain, you have to decide what you want to do, how far you want to go. So I'm sorry I have no clear answer. I know it's a bit frustrating, but it's not that easy. Okay, so I'm continuing then. The experimental design. You have nailed your hypothesis and all the variables that you're going to observe. Now the next step is to define the experimental design. And first term we need to discuss is validity. Or in other words, is there an English word for that? I guess how valid the results are. There are typically two kinds of validity that you need to consider. Exactly, that's the question. Do we measure what we want to measure? That's what the term validity describes. So I have internal validity, and this is the degree in which the dependent variable is free of the influence of confounding factors and only determined by the variations of the independent variable. Okay? Can you nod or shake your head? Okay, I take that as a yes then. External validity is the degree to which I can generalize the results to other settings, to other participants. So when I have students in my experiment, I can generalize to students, but it's difficult to generalize the results to professional programmers. Okay, the thing is about validity, you have confounding parameters. So parameters that influence the dependent variable besides the variations of the independent variable. So for our experiment on the commons and program comprehension, what do you think are confounding parameters? Do you have examples? Yes.
If it was students, the consumption of power drinks would influence
Okay.
comprehension.
Yes. Good. Yes.
Maybe also something like the level of education somebody got or something like this?
So maybe it's a graduate or undergraduate student that may have an effect, exactly. Yes.
Maybe something as simple as the monitor on which it's viewed.
Exactly, when you have these.
When you have this really old CRT monitor,
Yes.
you won't understand the code.
Other examples? Yes.
Sorry, I'm not sure if you are very used to know the language, for example, the programming language, it's maybe easier and you know much more without comments. If you're completely new to a programming language, then it's very hard.
Okay. Yeah, so how familiar you are with the programming language? Exactly. Max, you as well? No? Okay. sorry.
Also, natural language comprehension. So if the comments are in English and someone's not that proficient in English, that's a problem.
Exactly. Okay, so I guess we could here, everyone could name a confounding parameter and then another one, because there are really lots of these. So I did a study on that. So I looked at the papers who did a program comprehension study and looked at all the confounding parameters that they controlled for, that they mentioned, and this is just an excerpt. These are not all. So I found 39 of these. And more than half of them, they occur only because participants take part in an experiment. So they change their behavior because they are observed, their motivation drops, their learning effects, ordering effects, fatigue. They're afraid that they have been evaluated and all that stuff. So lots of stuff only happens because participants take part in an experiment. If you're interested in that, that's the paper. But I guess it's pretty boring because I just describe all the parameters and then after 10 or so, even when I'm reading it, it's okay. So you need to somehow control the influence of these confounding parameters. And there are these 5 common standard techniques. And I will discuss each of them a bit in detail. So first one is randomization. So I randomly distribute my participants to 2 groups. Maybe one group has comments, the other group has no comments. And there are dozens of techniques to do that. I can roll a dice, I can use a random number generator, I can toss a coin, I can let participants draw their number. And it's really easy to distribute the participants into 2 groups. But of course, I need a large enough sample. If I have like 10 participants and I want to distribute them to 2 groups, that's maybe not enough. Okay, and the second method is the matching or balancing, or the odd, even, odd, or the ABBA scheme, or the same method, just different names. So suppose I have here a number of participants on the left side, and here I measure somehow programming experience and I assign a value. And what I then do is I sort the participants according to this value, and then I assign the participants to 2 groups. And I just have the first 4 I assign to one group. Then I take the next 4, assign to another group, and then these and assign them to another group. And then do it in the ABBA scheme. So the first goes to group A, the second goes to group B, the third to group B, and the last to group A again. And this way I have somehow matched the two groups in this example based on their programming experience. What I can also do, of course, is I can use the first 4 and then randomly assign again the participants to both groups. So I can also mix the matching and the randomization scheme. Okay, then I have the matching. The thing is, once again, still the matching. The thing is here, I have to measure the confounding parameter. So, and this is not that easy as it seems. So how would I measure programming experience? What do you think? How can I measure this one? Yes?
Just a guess, but just check how many languages he's able to program in, and then, yeah, somehow get a number out of it.
Okay, so what does able to program in mean?
Yeah, how many different languages he's proficient in programming, but yeah, then it's also the question, what is proficient in programming? How good do you have to be be proficient? Yeah.
Exactly, it's not that easy.
And maybe grades in university.
I can use grades, exactly.
To say years spent.
Years spent on programming. So there are many ways to measure programming experience, and there's no agreed upon way when you do that studying computer science. So it's not always easy to measure confounding parameters. So programming experience, I can use questionnaires. So I ask how many programming languages are you familiar with, at least at a level of 3 when I have the 5-point scale, for example. I can use a pretest to let them implement something, analyze the results. Of course, then the experiment would get longer. I can use interviews. I can interview the participants. I can ask the supervisor of the participants. So there are many ways to measure programming experience. Another example would be intelligence. I can apply a test before the experiment, but then of course it would get longer, the experiment. The participants get fatigued more quickly. I can use university grades as indicator for intelligence, but of course, how reliable are university grades? Okay, so it's not always easy to measure a confounding parameter. Okay, now the third method is I can keep a parameter constant, so when I can't measure it. For example, for programming experience, I can't just recruit students as novice programmers. I know, okay, they just started programming or studying computer science. They might not be that familiar with programming. They are definitely novices. I can also only recruit programming experts, and then I can say, for example, okay, if you have been programming for more than 20 years, you know what you're doing, you are definitely an expert. And I don't have to measure it, I just make the assumption based on how I select the participants. Okay. Also with intelligence, I can select only participants that have a certain grade, and I can say, okay, you have a certain kind of intelligence, you're also good for the study. Okay, fourth method, I can use a parameter as independent variable. So I define another independent variable to the one I already have. So when I have 2 levels of one independent variable, so I have a comment and no comment the conditions, and I have another one, so like 2 levels of programming experience, high and low, and I suddenly have 4 combinations. So the design will get more complex. When I want to add another parameter, also with 2 levels, and then suddenly I have 8 conditions, and so forth. And now you can think when I have 39 of these parameters just with 2 levels, I guess I have more combinations than are people on this planet. Okay, so last one to control for a confounding parameter is to analyze the influence of the parameter on the result. And sometimes there are just situations where you cannot assign participants to groups, like when you want to observe two companies. You cannot just assign one developer to this company and the other to this company. You have to take them as they are. Or when you compare students from different universities, you cannot just assign the students to the universities. Also, often something happens during the experiment, like a power failure, or participants, they were just particularly noisy in that one experimental session. And then afterwards, you can analyze how much this affected then the results of your study. Okay, now there are 5 methods. What do you think? Which one is the best? Careful, it's a trick question.
It depends.
That's a good answer, I like that. Okay, when would you use randomization as technique?
You have a really large group of participants that would
When you have a large group.
Is there a minimum threshold?
Also a good question. I'm not sure. I haven't found anything in literature, but I have the feeling, so when talking to other people, that like 5 participants per group is too few, but 10 seem to be sufficient. So, but then again, when you have 4 combinations, you again need 40 participants per group. Okay, so when would you treat a confounding parameter as independent variable?
I mean, you really cannot handle or control completely that confounding parameter. You would include it as a dependent variable.
Mm-hmm.
When the parameter appears in a lot of tests, and we alter the outcome of the experiment.
Mm-hmm. Okay, and also when your sample is large enough, because then you have a more complex design, more groups, and you need more participants. Okay, I have a quick overview. So for randomization, when you have a large sample and you know the confounding parameters are difficult to measure, then really use randomization. When you have a small sample, you cannot use or should not use randomization, but then the disadvantage is that you have to measure the parameter, and that's a problem with all the other techniques. But my recommendation is that always when you have the resources, you have the time and you know how to measure a parameter, then use as factor. So treat the parameter as independent variable, because then you have a more general design, but also you have controlled the factors. But often this is not an option because you don't have the resources, you have troubles getting participants. Especially when you use professional developers, they typically want to get paid. I know of one working group in Norway, I think, and the professor there says that he rather has one assistant less than not being able to pay his participants. So for one study, they paid like 90,000 euros for 100 developers. That's pretty much. But then again, you have really results that you can apply to professional programmers. Getting students is easier. Yeah.
But if you pay this much to them, isn't this going to cause like a competition for basically a job of being participant, and then you have biased results?
No, they get not as much as they get when they just work. So they didn't get that much per hour.
Okay, because I remember reading somewhere that this type of compensations must be very low, so it doesn't it doesn't motivate basically participants to come participate for this award.
Yes. Again, you have to be careful to find a fine line. So also for students, typically what is interesting is to just have a raffle for an Amazon voucher or that stuff. So I did that once. I had like 40 participants. I had 3 Amazon vouchers, and then I could give them at least something. And I felt like really just exploiting them for the experiment. Okay. So now I need to come back to the term of validity. And I don't know if during the control techniques you realized that, but there's a problem with internal and external validity when keeping in mind these control techniques. You have an idea what I'm getting at? Again, there was internal validity, so the degree to which the dependent variable is free of the influence from any confounding parameters. And then I have external validity, the generalizability of my experimental setting. Now, what if I just keep the influence of all confounding parameters constant? Do I have high internal or high external validity in that case? Yes. Exactly, because I just controlled everything and I really have a highly artificial setting. Okay, but what's about external validity? What does that require? Yes.
Well, it requires that the confound barriers.
Confounding parameters? Sorry.
That they can change because they're not always the same. So if you always have the same parameters, that means you can't generalize it because it's only applicable to the one case that you study.
Exactly. So you have this fundamental trade-off between internal and external validity. Internal requires that I control as much as possible, and external requires that I am not controlling anything, kind of. So what do I do with this trade-off? How do I handle this one?
We're taking a large enough sample that is representative of what you want to measure, but at the same time it's not so large that you cannot control it.
Okay, that's practically impossible because I would need more people than are on this planet.
Doesn't it also change about the method you're using? Because I think if you use matching, your internal validity is rather high because you already looked at them and already matched them. But if you use randomization, you control nothing because you just randomized them, so your external validity is rather high.
Exactly. When your sample, again, is large enough and representative enough. So you need students and professional programmers, for example. Yes, that's one way. Yes.
Would it be helpful to get an average of these parameters so that you could say, okay, this is the maximum value that it could have, or the worst value that it could have, and get an average and maybe use that to make it generalize?
Well, you could do that, but then again, you need a large sample because you somehow need to distribute the participants. Yes.
Okay. I think traditionally the way it was, at least I can tell you from economic theories, for a long time people just concentrated on one or two most important independent variables, and they thought, okay, everything else will be constant for now, and they held all of their experiments, or they came to a theory like that, and afterwards these theories were validated externally, and then the flows were basically found doing the external validation study, so to say, and then you can find what the flows are and try to concentrate on these factors and see how powerful these are.
Exactly. So basically, you cannot do this in one study. That's impossible. So basically, what you do is you do lots of studies. So again, that's how it's done in medicine or in physics. So you first maximize internal validity. Then you really get an understanding of how the variables interact, how the variables affect each other. And then in subsequent experiments, you can step-by-step increase external validity. So for example, you can do a study first with just beginning programmers, and then you can use different levels of programming experience. So like graduate students, they have certain level of skill, then professional programmers and then the really, really professional programmers. Then you have step-by-step increased the generalizability of your results. Okay? I know it's hard, especially when you need to publish the experiment, not to really to do that, but that's the way to address this trade-off. Yes?
So I'm wondering, of course the ideal situation is controlling everything, but now in reality everything is probably not feasible, and if I want to publish something, how do I even show that I have possibly thought of everything? So if I know every confounding factor and I do have the resources to control them, okay, but then how do I get there in the first place, knowing about everything? How could I show that I have done a good job of identifying these in the first place?
Well, it's then again how you write the paper, right? You have
I'm thinking actually about the actual research. So what should I do in terms of identifying these in the first place?
Oh, identifying. Yeah, that's again typical question. Difficult question. Well, what I did is really look in the literature on program comprehension studies, several venues over a time span of 10 years, and then I really looked what confounding parameters are there. Then I know, okay, these were controlled by the authors, and then I get the feeling, okay, these must be important. But of course, I can never be sure that I really captured everything. And the second step is really to look into the literature on designing empirical studies. So I have some recommendations in the end, because there are a lot of parameters that occur only because participants take part in an experiment. So again, it's literature research and also, of course, just plausibility. I mean, you're an expert in your research domain, right? So I'm really familiar with program comprehension, and then I get a feeling what factors there are that influence program comprehension. Like programming.
It's not a good argument.
It's not a good argument, no, but that's a good starting point. I know, okay, they are important, they should be important, then I can look in the literature, really, are they important? So you have to really read the literature about that. I know it's not a nice answer, but that's, yes.
So in class we discussed the trade-off between rigor and relevance. So how closely is rigor associated with internal validity and relevance with external validity?
Okay. Okay.
So are you saying yes? So you say rigor is closely associated with internal validity, and if you want to publish, rigor is more important than relevance, versus where if relevance and external validity and generalizability is closely associated?
No, it's not a one-to-one mapping. I mean, relevance might also be important if you want to publish the results. So that's something I will talk about later this day. So about the expectations of reviewers on the relevance of what you're doing. So they're good internally valid studies. They're really interesting, really well designed, but of course the conclusions you can draw from them there are really restricted. But then when you have practically relevant studies, so I know one study, they just observed professional programmers, not many of them, like 12 or so, for 45 minutes. And the programmers were doing the self-selected task, like looking at code, writing documentation, fixing a bug. And the programmers talked aloud during that study. And then they derived just a lot of hypotheses about what programmers do and how they proceed. So like that they're really goal-oriented, so they focus on getting the task done. They use a lot of additional tools, not the built-in functionality of their IDE. And that, I think, is a good example of an externally valid study. It's relevant, but it's not that rigor. So you can go either way when you do when you want to publish your results. Okay, any more questions? Okay, so now I'm going to talk a bit about experimental design, so how you arrange your participants. You can divide them in 1 factorial and 2 or more factorial designs. 1 factorial means you have 1 factor, so 1 independent variable. And I guess the first thing that comes to your mind is this A-B comparison. So you have one group who works with comments, the other group works without comments, then you compare these two groups. And this is a between subjects design because you make comparisons between the subjects. And the difficulty here is to create comparable groups. If your sample is large enough, okay, you can just use randomization. But if you have a small sample, you need to somehow you should use matching then and be careful about how you arrange the groups. Okay, the second variant that you can use is the within subject design. So you use one group of participants and in the first session they work with comments, in the second session they work without comments. So it's within subjects because you compare subjects to each other. What's the issue here? Yes?
You already have experience from session 1 and could take your experience you learned in session 1 to session 2, so the results aren't that valid probably.
Yeah, so you have learning experience, but you have to take care of that. So it's a confounding parameter, and you need to control for that one.
Well, you have few different source codes, but one's could be just more difficult to understand by
Yes.
the program. So you can't really make sure that they're the same.
Yes, and that's the difficulty in designing such a study. When you use a within subject design, you need to make sure that they are comparable in their difficulty, but again, not too similar that participants can use their experience from the previous study. Also, ordering effects, maybe that plays a role how the participants started. So if they're used to comments and now there are no comments, maybe that makes them slower than if we would have started with no comments and then they could use comments. So do you have an idea how to improve both designs? So in fact, I can just combine them. We call it the Latin square design. So I have between subject and within subject. So I can compare between these two groups, but I also can compare within two groups. I can also look for ordering or learning effects, because when the difference in session 1 is different compared to the difference in session 2, like when I say this one is larger than this one, then there are clearly learning effects somehow. Okay? You're smiling? So you're having fun, that's good. Okay, what are the issues here? I guess it's so easy if you combine these both designs, you have the same issues that you have for these two, you have them here as well. So we have learning effects, but the good thing here is you can analyze the results regarding that effect. So you can look at the size of the difference and see how strong learning effects they are. You have mortality. That sounds a bit weird, but it's just describes the effect that participants just drop out. They don't come to the second session. I know it's a weird name. Psychologists use that. Okay, then there are 2 factorial designs. So when I have 2 or more factors, in this case I have a comment, a no comment, and programming experience high and low. Then again, of course, I have 4 groups. This again here is the between subjects design. And of course, I can make this within subjects design and have all the groups. But you typically don't want to do that because you need many participants, you need much time, and the analysis gets more complicated. And yeah, so which design should you choose? Which design would you choose when you have a question to answer? Yes.
If you have enough participants, probably this combined metrics, because with a rather low amount of participants, you get a good outcome, I think.
Mm-hmm. Okay. The correct answer is, as always, it depends. So as you said, when you don't have enough participants, you can use the within subject design because you can then reuse your participants for the second session. If you have enough, you can use a within subject or use such a Latin square design because it just lets you do more with the results. You have a better way to interpret the data. Okay. Questions so far for the experimental design? Okay, now we have planned the experiment, we have the hypothesis, the variables, we have the participants arranged in group, we have taken care of all the confounding parameters, and now we can execute the experiment. So what can go wrong? Everything, exactly. So when you do your first experiment, something will go wrong, no matter how good you prepare. So what you definitely need to do is do pilot tests. Test the material that you have, so test the questions that you're asking. Do participants understand what they have to do? Test all the tools. Are they working? So for one experiment, I implemented a tool to display the source code. And I tested, like always, the first 2 minutes or so, worked pretty well. But beyond that, suddenly the line numbers start to scroll up and participants scrolled the source code, and then okay. I didn't test that. Also, I did pilot tests, and I had 6 tasks there. And then the result of the pilot test was that I need a warming up task to let participants familiarize with the setting, that they know what they're doing. And then for the original experiment, I forgot that I had 7 tasks now. So all the questionnaires that I have, so how difficult did you find the task? They only worked for the 6th task, but not for the 7th task. And of course, there's only a participant during the end, so one of the last, who submitted the results said, hey, you only had 6 tasks here in the questionnaire, but there were 7 in the experiment, what should I do? So, yeah. Okay, also test the data storage. So I implemented another tool for the data, and so for conducting the experiment, for customizing everything. And one participant, he just didn't properly finish the tool. He just used the X to close the tool. And then the experiment was aborted and the data weren't stored. I didn't know that. I just found that out when I was trying to get the data from this participant. Now that tool works better, the data storage. Okay, very, very importantly is you need to tell participants exactly what they have to do. So if they don't know what they're doing, they really can get angry at you because they're frustrated, they are confused. So in one experiment, they had to use different Eclipse versions, and they weren't sure which one to use, and then one really got angry because they really didn't know what to do, and they feel their time was wasted, and they really got angry at us. So a good thing here is to use really a warming up task, so really exercise the task, the proceeding one time together with the participants, show them each click that you're doing, each answer they should give. Really, you can't think stupid enough for the participants. I know it doesn't sound nice, but really, just to be sure that they know what they're doing, do a warming up task with them. It just can be a hello world example. It's sufficient. And then another thing is that you really have to observe that participants are just doing what they're supposed to do. So in one experiment, I implemented in a browser, and participants were not allowed to use the search function. So they were not allowed to use in the search in the code for specific names. And of course, there were people who didn't know that. They were surprised when I told them, hey, you were not supposed to do that. What, really? And another one, he was more clever. He copied the source code in an editor and then used the editor search function for the source code. Yeah. So really observe the participants, what they're doing. Also make backups of the data. So I lost lots of data. No, I lost some kind of data on that. So really, secure your data. Be sure you have them on different locations. Okay. A few words about ethics when you treat your participants. So always the first thing, be nice to your participants because they voluntarily invest the time for you. So even though the participants used the search function, I still was nice and explained them they were not allowed to do that. I had one participant who was finished after 30 minutes for an experiment that lasted 2 hours. So I know, okay, he wasn't motivated to participate, but I still thanked him, and then, yeah. So really be nice, it's really important. Also assure anonymity, especially when you do it in a university context as part of a course or so. So make sure that the professor never gets to map the data, the performance of the experiment to the students, or you, if you well rate the students afterwards, if you give them grades, be sure that the data are anonymous. Also assure that the benefits for science is worth the effort for participants. In computer science, it's not so much an issue, but again, if you value a teaching method and you know you have this brilliant, new, really productive teaching method that really helps students to learn programming, you have to ask yourself whether it's nice to just have one half of the course experience the new teaching method and the other one, the old boring teaching method. It's more, in medicine, this is more of an issue. So I heard of one experiment where there were operations on the knees, so participants had some issues with their knees, and there was a placebo group. They just cut open the knees and then sewed it again, they fixed it, and then the participants also felt better. Highly questionable, yes. And if you're not sure about that, there should be an ethics committee here at the university, so consult that. Also in the US, when you do an experiment there, you have to consult an ethics committee. You have to do a lot of paperwork to get it approved by them. Also let participants fill out a consent form, all that stuff. So it's easier here in Germany to do the study. Okay. Oh yeah, if you're interested in that, there's some nice information. Okay, so now for the analysis. So I have these two versions of the source code, one without comments, another one with comments, and then I have this data. So I measured the response time in seconds. Participants should determine the result of the system or printline method in both cases, and then measured how long they needed. Now, what do I do with the data? What would you do? Yes. The average. Okay?
So of each group.
Of each group, the average, and then compare the average. Okay, so one is about 50, the other one is about 39. I guess group A is then 50 and group B is 39. What else? Yes?
You want to look at the variance in the groups?
The variance or standard deviation.
There are some answers online, so min and max. You can look at the minimum and maximum.
The
of each
minimum,
group.
maximum, okay. Okay, so basically what you all just said is describe the data. So standard stuff is median or average. You know the median, what it is? Okay, I'll just skip the example. Standard deviation, we just go through all that, and the box plots. Okay, so the median is just the value that lies just right in the middle. So I have the data, sort them, and choose the middle value. You're so critical.
Is the table correct because it's all group A but 2 times?
Yes, so one time is not sorted, the second time is sorted.
Oh, okay. Well, that makes sense.
Okay, just to illustrate the... okay, so median is here 49, and when you have an even number of participants per group, you can maybe compute the arithmetic average between the two ones that are close, or some statisticians say that the median really has to be in the sample, and you can just choose one of these. Okay, You know the concept of standard deviation? Okay, so I just skipped that one. And you know box plots, right? Okay, so I just skip that one. If you have any questions or online questions.
I will follow.
Okay.
I think, why do you assume that this is a Gaussian distribution?
That's the assumption of all these, of the average, of the standard deviation. That's the assumption of the normal distribution, yes.
Vice versa.
I'm sorry?
If you have the standard deviation, then you can do it, but why do you not say it's different? Okay, we can skip that.
Okay, I'm just assuming that for standard deviation and for the mean, you need, of course, normally distributed data. Then it doesn't make sense to use these values, right?
But why do you assume that you have normally distributed?
I don't assume that. I just say they have to be. Okay, on the data, I don't think they're normally distributed. Okay, so statistical tests. Are you familiar with these significance tests? Okay, so now something new. Okay, so these are the arithmetic averages between both groups, for both groups. And the question is, these are 11 seconds. Is this a real difference? Is this a coincidence, the difference? Does it happen because of the experimental setting, the group size, all that stuff? So I'm not sure. And to be more sure, I can do a significance test. So, and the assumption for each statistical test is the null hypothesis. It's the assumption that both values are equal, so they're both the same. And then what the test computes is the conditional probability to have this result under the assumption that the values should actually be be the same. So what is the probability that I have this 11-second difference, although I assume that the difference should actually be null? Okay? And then if the probability is low enough, then I say that the assumption must be wrong. So then that the null hypothesis cannot hold. And what low enough means, there are different thresholds. The most typical one is the 5% threshold. So if the probability that the values, if the probability that the difference is 11 seconds is below 5%, under the assumption that they should actually be the same, then I cannot hold the assumption. What I can also do is a 10% probability. What do you think, and which circumstances does that make sense? We shortly talked about this.
Maybe the data set is small.
No. Yeah, so the bigger the sample is, the lower the p-value will get. Yes, but in that case, no, you shouldn't do that based on your sample.
Well, if you were fishing for a result, you could just increase this value a bit, and then the hypothesis stands.
Kind of, yeah, you're right. So actually, sometimes I read the results are marginally significant when they're between 5 and 10%. No, but the interesting case is when you're exploring, when you have no idea about the relationship, how variables interact. You can set a 10% probability. Do you know why it's in this case it makes sense? Yes.
Just a guess, because you don't really know how good your hypothesis is, because you don't know the output, so you don't really know how good your hypothesis was in the beginning?
Kind of, yeah. So you don't want to dismiss any interesting effects. So maybe the experimental design was not sufficient enough to capture really the hypothesis or the relationship between the variables. And in this case, you want to be more lenient. You do not want to dismiss a possible interesting effect. And then what you can do, what you definitely should do in subsequent studies, is look into this effect deeper. So as a rule of thumb, when you're exploring, you're doing initial studies, there are no data available on that yet. It's okay to set a 10% probability threshold and then look deeper into the data afterwards. Okay? Yes?
So do these probabilities vary depending on the sort of criticality of the output?
Yes, definitely. So I guess you guys remember the discovery or almost discovery of the Higgs boson, the most likely discovery. They have a really, really low probability of, I don't know, 0.0001 or that kind of probability. But they also have lots and lots and lots of data. They have lots of data on that. That's why it took so long to really announce the discovery, because they had years of data, I guess. Also when how critical the results are, maybe when you try to get a new drug approved for medicinal use, you also want to be very careful with that. You always have to weigh in the benefits of rejecting or accepting the null hypothesis. You always have to weigh these. But typical in your case, it's 5%, and it's standard. You can't do much wrong with that when you say 5%. Okay, so in this case, I did a t-test on the data. This is one significance test. There's dozens of significance tests. I have some literature in the end with nice overviews. So interesting values for the t-test are the p-value, so is it lower than the 5% or 0.05? And for the t-test also it's not that important here, so the test size. But when you report such a result, you always need the p-value, the test size, in this case the t-value, and sometimes also the degrees of freedom. But that's just a side note for later. Okay, now if the p-value is larger than 0.05, there's no significant difference. And when it's smaller or equal to 0.05, then you have a significant difference. And now the question is, what does that mean? So in our case, the p-value was larger than 0.05, so the 11-second difference is not significant. So, but if you have a significant difference, it's really interesting to understand what these results mean. So you can never say with a statistical test that you confirmed a hypothesis, because all you have is a conditional probability. You don't have any deterministic results, it's just a probability. So we could, in this case, we do not confirm a hypothesis, we just couldn't find any evidence against it. That's what you can say with a statistical test. So what you should never say or write is that you confirmed a hypothesis, but that you maybe accept a hypothesis, or when you want to be more correct, you can only make statements about the null hypothesis, so you can either reject the null hypothesis or you cannot reject the null hypothesis. Okay? It's really important to understand this difference. You cannot confirm hypotheses, just find evidence against or for it. Okay. I'm going to skip that. So you need some preconditions for the test, for all significance tests. If you have questions about that or interested, we can just talk about it later. So there are a lot of further tests. These are the standard tests. If you're aware of these, know how to apply them, you can really get far with the data. So again, if you're interested in that, we can talk about it later. Okay. So now for the interpretation. So what do the results mean? So I have observed a difference of 11 seconds in favor of comments, so that comments speed up the comprehension process. So what do these 11 seconds mean? And that's really an interesting question. So what can I do with a difference of 11 seconds? What do you think? How would you interpret this difference? Assuming it was significant, maybe that's easier for you. Yes?
Just check how much the 11 seconds of the total amount of time were, and then you could maybe say that it's 20% maximum absolute numbers. Not because if it's 11 seconds from 1 hour, it's not really significant, but if it's 11 seconds for, as we've seen, 50 seconds or something, then it's a big difference.
Mm-hmm. Okay, so look at the complete time, yeah? Now, would you recommend with a speed up of 11 seconds to companies now that they require their developers to always write comments at the source code? I see some head shaking, so of course not. And why? What's the issue here? Yes.
so much time that the 11 seconds you gain wouldn't be feasible financially.
Exactly, you have to write the comments. And then if the time for writing the comments is so much larger than for the speed of comprehension, then of course it's not worth writing the comments. Yeah, also, did anything happen during the execution? Were any participants, were they annoyed or anything? So for the first experiment I conducted, so I evaluated the effect of background colors when I highlight the source code or specific parts of the source code with colors. And we expected that for certain kind of tasks that it wouldn't make a difference because participants would look into the source code in so much detail that it shouldn't have an effect. But then for one task, we found that participants with the colors, they were significantly slower in the comprehension process. And then we were, of course, a bit confused. But then, we noticed or we remembered that participants for the colors, they were really moving close to the screen. And then we looked at the task again and we found that the class for this one task was completely annotated with annoying red background colors, really the complete class. And participants really moved close to the screen to recognize the source code. And this, of course, after time caused visual fatigue, and this made them slower. But we only noticed that because we observed the participants during the execution. And also, I think one participant noted that afterwards. So always ask participants afterwards what they think, even if it's just informal. So what was your experience? Did you have fun? But also a good idea is to have like a questionnaire, an open question. So do you have any comments about the experiment? And encourage participants to really complete this questionnaire. And also it's important to interpret the result in terms of practice. So what does that mean? Should we write comments or not? And this is something that it's really difficult. I mean, all the other stuff up until the execution and analysis, I guess it's pretty intuitive. Of course, I have to think about all the confounding parameters. Of course, I have to look whether difference is significant or not. But then interpret the data is really difficult because there's no standard procedure for that, but it always depends on the research hypothesis that you have. And this requires really a lot of practice. And also when you look at research papers, they often do not a good job on that. They do not interpret the data. And this is something it requires practice and be careful about that. It's really, really important to interpret the data. Okay, so how do you feel now when you want to design an experiment? Yes?
A degree of trepidation.
I'm sorry?
A degree of trepidation is that you're in fear because you always have to evaluate what's the pros and cons, every single decision, every single step.
Okay, so I guess you feel a bit frustrated. You have the feeling like, okay, there's no perfect design for my question. And you're right. There is no perfect design. You always have to decide for your case what you can do with the resources. You need to accept that every experiment has flaws. There is no perfect design. It's unavoidable. There will always be something going wrong in the experimental execution. So do not look for the perfect design, but look for the best design in your case. Look at the resources you have, the time, the participants, you have the questions that you want to answer, and then choose a design that's optimal for your case. So I also felt this way when I finished my first semester, and then I said, okay, why try? Why even bother with experiment design? But once you've finished with that stuff, once you have overstepped this obstacle, then you can go and start planning really good experiments. Okay, so I have some literature. Really interesting, really good is this one here, the experiment design part. They really explain in detail with examples how to conduct how to plan experiments, how to take care of confounding parameters. Thing is, you can't order this one anymore online, but good thing for you, this was published here at the university, so it definitely is available, and I guess Dirk also checked it. It should be here.
They told me it's 15 volume.
It's 10 volumes, yeah.
10 volume, okay.
But it's, no, it just feels that way, so it's really a big folder. But it's only half a page is printed. And then you have a lot of extended material, a lot of readers, so it's in 2 or 3 days you're really finished with this. It's really a good read. And this is really the best introduction to experimental design, so I haven't found anything that's nearly as good. Okay, there's stuff in general on experimental design. So this first one is for research more in psychology with more details. This the Volin. When you're doing empirical research, you might step about this name, and this is experimentation in software engineering. It's really a nice summary and overview, but it's really abstract. So it's not that good and really helping you understand how you should design empirical studies. And then the analysis. These are pretty standard books, one in English, one in German. I'm only really familiar with the German book, and it really explains all the statistical tests, all the assumptions, all the descriptive statistics, and really with examples. So really by hand you can compute all the examples of the statistical tests, get really a good understanding of how they work and why they work. Okay, so I'm finished. And now, if you have any further questions, just ask. Yes.
I have some questions.
Some.
Yeah. Well, first, it was interesting about the think aloud method in the beginning, and I've seen how to test website usability, this is often used. So they just get someone, and this person is trying to achieve some task, and is talking what he is or she is thinking while he is doing this. But it always seemed to me that this is like very effort-taking process.
Yes.
Do you think it's worth it?
Yes.
Yes?
Definitely. But again, it depends on what you want to analyze. So in the study I mentioned with the professional programmers, it was really worth the effort because they got a more understanding of how developers proceed when solving a problem. If you want to observe whether comments speed up the comprehension process, of course it doesn't make any sense to use that because you just want to know, is it faster or not? So every time you want to learn something about the cognitive process, about the thoughts, how it proceeds, then it's very interesting and it's very good. And also participants get used to talking aloud. So after a couple of minutes, you really have the unbiased thought process. But of course, yeah, it's annoying to analyze all the data.
Okay. So I like this p-value, obviously, analysis to the statistical analysis, basic stuff. But how do you calculate the error margin there? Is there a good practice to calculate the error margin, or do you just use the standard deviation to say, okay, this is how much it can vary, basically? Or are there other methods for this?
I don't know. I don't think there's a kind of error margin that you can compute. But you need to select the right statistical test depending on the data you have. And what you then can also look at is the effect size. So the size of the effect that you have. In our case, we had response time. It's pretty easy to interpret, but there's also a standard way to compute the effect size based on the difference between the arithmetic means and the standard deviation. And then you can also say how large the effect is. And this also helps you to interpret the data, the results of the significance test. And this is what you always should do afterwards. After you have a significant result, also look at the effect size.
So controlled experiments count as the classic scientific method. Does all research end in controlled experiments, or are there other research methods that you also use in your research?
There are also lots of other research methods. So what I like to do is some kind of qualitative study. So really just observe participants without all these extensive planning. Of course, you need to have an idea what you want to observe, what the results are that you want to do. But this gives you a bit more freedom during the experimental session, what you observe. And if you know that or notice that during the execution some interesting effects, you can also look for this in more detail.
So one more question, please.
So When doing the control experimentation, it's always, or it's probably more expensive than other forms of research.
Depends.
Depends. So when should I really decide to do an controlled experimentation? How do I decide when to do that and when to maybe try something qualitative?
Well, that's a difficult question because again it depends on the resources that you have and on the experience you have and on the status of the research. So if you're really in the beginning and you have no idea how anything could be related, it's okay to start with a qualitative study and really collect everything and then look in the data, do you find something? Of course, don't drift into fishing for results. And then go more like for the controlled experiments part. When you have a really concrete idea, so like with the common stuff, it's really concrete, then you can go for a controlled experiment. So again, let's decide on the circumstances.
All right. So thank you very much.
Thank you.